In this video, we are going to discuss current division. Similar to voltage division, the current division principle allows us to determine the current through a particular resistor directly without applying Ohm's law. So let's take a look at this circuit example. We have a current source, I total, or I'm going to represent it as IT, and two resistors in parallel, R1 and R2. Now, all three components are connected in parallel. So you have one node up top that is common to all three, and you have one node at the bottom that is common to all three. So the voltage is shared and is the common value for all three components, right? So voltage V is common to all the current source, the resistor R1, and to R2. Now, there's a small derivation. The derivation simply states that we find the total voltage V first, and V would be given by the I total times Req. Right? Now, Req, of course, Req is the total equivalent resistance of the entire network. Whether that network has two resistors in parallel or 2000 does not really matter. It's the total equivalent resistance of the parallel resistors. All right. So in this case, it's a simple circuit. We have two resistors, R1 and R2. So Req is given by the parallel combination of R1 and R2. And when you have two resistors in parallel, it's simply given by R1, the product of the two, R1, R2, divided by the sum of the two, R1 plus R2. All right. Anyway, once you have the voltage, you can now apply Ohm's law to find I1 and I2, right? You can now apply Ohm's law to find I1 and I2. So from Ohm's law, I can say I1 is equal to V or R1, and I2 is V over R2. I plug in V or substitute V from the above equation, and I can get I1 is IT times Req over R1, and I2 is IT times Req over R2. So similar to voltage division, I can describe current division principle as when you have a current that is applied to a parallel network of resistors, the current gets divided across through each resistor. A fraction of the current flows through each resistor, and the fraction for each resistor is given by the ratio of the total equivalent resistance to the resistor itself. So a fraction of IT appears flowing through each resistor R1 and R2. The fraction is given by Req to the resistor, which is R1 and R2. Okay, it's the opposite of voltage division. In voltage division, you have the resistor in the numerator and Req below in the denominator. In current division, you have Req up top and the resistors R1 and R2 at the bottom. Okay, so let's look at an example problem. In this circuit, we have three parallel resistors, and we have a 15 amp current source. So it's being divided into three. Now let's find all three currents, I1, I2, and I3, by applying current division. So I would say from current division principle, I can say I1 is equal to IS times Req over R1. I2 is IS times Req over R2. And I3 is IS times Req over R3. Now, Req is given by the parallel combination of R1, R2, and R3. And so that would be 1 over 10 plus 1 over 30 plus 1 over 60 and the reciprocal of those sums. Total REQ comes out to be 6.66, well, 6.666667, however long you want to make it. Again, note that 6.667 is smaller than the smallest resistor in the circuit, which is 10 ohms. So now I plug it back into the equations and I can get I1 is equal to 15 times 6.66667 divided by 10 and gives me I1 as, let's see, 6.6667 divided by 10 gives me 10 amps. Whereas I2 will be 15 times 6.6667 divided by 30. So I2 is equal to 3.33335. And I have I3 as equal to 15 times 6.66667 divided by 60. And that gives me I3 is equal to 1.6667. And of course, when you add it all up, it should equal approximately 15 amps. So there you have it. That, in short, is current division.